Hello, everybody. Welcome to our session today. We have a really exciting session for you, as always. I see people are still joining, so I'll give it about a minute or two. So if you need to go to the restroom or get yourself some water, right now is the perfect time. And we'll start at 3:02. Thank you. Okay, welcome everybody. We have a really exciting session for you today. We're going to be discussing refining flexibility and rigidity of fully and semi-integral abutments. For anybody who is new to our sessions or new to our company, we are a subsidiary company of Midas IT, and we develop a total solution service for bridge building, geotechnical, and mechanical engineering. If anybody is new to this platform or hasn't used it in a while, there was an update uh, earlier this year, so I just want to go through it really quick. In the middle, you'll have the presentation screen. If there are any cameras activated, like there are right now, you'll see them at the top. And then any settings, any quick settings that you need to update can be found using the buttons at the bottom. Using the hand raise icon on the bottom left, you can not only get our attention by raising your hand, but you can also react to the session at any point. You can use the question box at the top right to submit any questions to the speaker, or if you have any questions about Midas itself or anything that you would like to submit, you can do so through there. And then any more in-depth settings, you can use the little gear icon and toggle with your microphone or speaker or anything like that. So I'm going to go ahead and introduce our speaker today. We have Mohammed, who is an engineering manager working for Parsons Bridge Division in Vancouver office. He has over 25 years of experience in bridge engineering in Bangladesh, Canada, and the United States. His work experience has focused on pre-stressed and post-tension concrete girder bridges, steel plate and box girder straight and curved bridges, precast segmental concrete extradosed and steel plate girder cable stayed bridges, and three-dimensional finite element modeling. His expertise is in analysis design, detailing erection, evaluation, load rating, rehabilitation, and construction of bridge structures. He has successfully delivered complex bridge projects in less than the anticipated budget while maintaining a high quality standard. He is experienced in the conceptual, preliminary, and detailed design of short to long span concrete and steel bridges. His innovative design solutions has significantly saved construction and maintenance costs. He achieved his master's degree from McGill University in Quebec, Canada, and he is a licensed professional engineer in the provinces of Alberta, British Columbia, and the state of Washington. He is the author and reviewer of numerous technical papers on bridges and structural design. So without further ado, I'm going to go ahead and make you the presenter. You should be able to share your screen, Mohammed.
Thank you so much, Luciana, for nice intro. I'll turn off my camera during present for a smooth slide presentation and then back later. But now let me just share this first. Can you see full screen?
Yes.
Okay, excellent. Thank you again, Luciana, for giving me an opportunity to share this presentation with you. Redefining flexibility, rigidity of fully and semi-integral abutment. Actually, this presentation first presented 2022 at Short and Medium Span Bridge conference in Toronto. Still, it is 2 year old, but the concept or the content of the presentation is always new. So I hope you will enjoy the presentation and it will be applicable in your daily design task. So agenda of the presentation is introduction and background, traditional and isolated abutments, various pile foundation, structural behavior and flexibility, stiffness and strength of piles, result and discussion on case studies, definition of integral abutment bridges by the code, consequence of unclear code definition, example of integral abutment bridge without code specified piles, and finally conclusion and recommendation. So introduction and background. The abutments are major components of bridge structure. Traditional abutments are mainly classified as fully integral, semi-integral, and conventional. In recent years, a new type of isolated abutment has been developed and built in Vancouver, BC. Integral abutment bridges eliminate expansion joints, therefore known as a jointless bridge. IBs are less expensive and almost maintenance-free. IBs are becoming more popular day by day. First IBs was built in 1920 in Colorado, USA, and the longest IB also built in Colorado, USA. So now look at the traditional abutment types. So basically three traditional abutment types we use: fully integral, semi-integral, and conventional. So fully integral is basically all the superstructure, substructure, and the foundation are integrally connected. With the full integral abutment, we have to have a single line of pile to allow more flexibility. And that is the fundamental requirement of the fully integral abutment. So pile could be within the casing or without casing, depend upon the soil movement, but most of the cases we need casing to allow the deformation of the pile. When the loads are very high, the spans are a little bit longer, a single line of pile may not work. In that case, we have to go with the double line of pile, or in that case, we have to have a bearing top of that, because when you go with the double line of pile, the behavior does not work as a full integral because of the pull and push of the double line of pile. So we introduce the bearing to allow the rotation. Uh, that is the semi-integral abutment. We call it semi-integral abutment. And then the conventional abutment, which is basically the old days bridges, a multi-line of pile with bearing and the expansion joint. And this expansion joint basically cause a lot of problem to infiltrate water through the that expansion joint to the bearing and the substructure. So, but probably some cases we cannot avoid this one. So we have to have the conventional abutment bridge, but for short span bridge or up to around 200-meter long bridges with multiple span, we can go with the fully integral abutment bridge. So another abutment is recently introduced in BC, Vancouver, and we call it isolated abutment bridge. And for integral cases, we can call it isolated integral abutment bridges. And you see at the top, there is a traditional integral abutment bridges where the piles are inside of the MSC wall. That means we need a longer span to have the, for example, 40-meter clear width. But if we want to keep the same clear width, 40-meter, we can reduce the span just to bring the pile, call it as a isolated abutment or typical pier in front of the MSC wall. And the traditional approach slab, we can call it as a jump span or jump slab because we have to have design of the approach slab as a simply supported case without considering any soil support underneath. So design-wise is the same, but we can have some advantage if we choose the isolated integral abutment. Only the problem is we are losing the restraint of the soil during the longitudinal movement in seismic cases. But in that case, the fundamental assumption the embankment must not be collapsed so that we can allow the restraint by the embankment. But if we go with the isolated, we cannot use that soil restraining effect. But other than that, we have some significant advantage. In the next slide, we'll see the advantage between two abutments, isolated abutment versus the traditional integral abutment. On the left side, you see the traditional integral abutment. On the right side is the isolated integral abutment. And the advantages are no back wall required, no wing wall required, reduce span length as we see in the previous slide, reduce weight. So when we reduce the span, we reduce the weight. When there is no wing wall, we reduce the weight of the abutment. Reduce the number of ply. As the weight reduced, number of pile also reduced. Provide extra space. So this space can be used as a walkway or for the maintenance vehicle. Reduce approach field. So we don't need the approach field dislocation. So that is reduce the cost. Avoid constant construction overlap. So that means the bridge and the approach can be constructed without depending on each other. Increase performance, definitely it provide a bit better performance than the traditional one, and overall it reduce the life cycle cost and easy to inspect. So for example, if we go for the design for the seismic design, and if we allow the plastic hinge here, it cannot be inspected. So basically in-ground hinging is not recommended by the many code. So in that case, the isolated abutment, we can easily inspect it, allow the plastic hinge here. So that is one of the another advantage. So we can easily inspect and repair. So now we'll talk about a little bit about the detail of the jump span. Jump span is nothing but a typical approach slab. So for a small movement, we can use the thermo joint. It is supported one side on the abutment, or we call it typical pier bend, and the other side is the slipper slab. And for the large movement, we can use the transflex seismic joint like a steel plate and the modular rubber. So it's allow superstructure to move transversely and longitudinally to improve seismic performance. So this is option one. Option two, we did a similar thing, but we can allow to kick off this um, approach slab or the jump span so that we can get some energy disruption here. So that is another advantage of this one. So for service load or service expansion and contraction, we can use a joint seal here. But for the large movement in seismic event, we can allow to kick off the jump span. Now we look at the various pile foundation for integral abutment. So first is the HP pile, which is very commonly used for small span bridges, which is like a HP pile, different size, 360, 120, 360, 152, and 174, and 1 feet diameter of unfilled steel tube. Currently, the Canadian code 614 and 619 only restricted to use this pile for integral abutment bridges. And then in BC, we commonly use the 610 or 2 feet, 914 3 feet diameter concrete fill steel tube, which is very popular by the contractor and the client or the MOT. And another option is the board pile. It's a concrete board pile. So, for example, 750 1 meter or 1250 diameter cast in place reinforced concrete board pile. And all cases, the pile can be encased with the casing. So, for example, we can use the CSP casing and fill with the styrofoam beads. This is very typical. For the large diameter of pile, we can also use the concrete manhole pipe and the styrofoam bead to allow the movement of the pile. So this is the example of the casing and construction steps, integral abutment bridges and approaches. Most of you are familiar with this, just try to refresh the mind. So excavate approaches, drive and drill piles, install casing, fill styrofoam bits, install MSE wall in layer, install strap in layer, fill approaches in layer, compact fill in layer, and then repeat step 5 to 8 as needed. So this is the HP pile with the CSP casing. And the bottom one is the concrete pile with the concrete manhole pipe to provide some movement. Uh, So this is the fundamentals of the simply supported bridge, fully fixed end bridge, and the integral bridge. So on the left side is a simply supported bridge. So it is in case and the supports are always free to rotate. We don't have any movement, so all the we don't have any moment, but we can allow the movement at one end, and the friction, we cannot find any frictionless bearing, so there is some friction, of course, so that's why we'll see some kind of axial force effect, but those are very, very minimum. But on the fixed end bridge, all these axial forces are restrained in theory. So we'll develop a huge amount of axial force on the superstructure. But we have to allow this movement during the thermal effect. So we cannot restrain that movement, otherwise we'll develop a huge amount of axial force, and the superstructure can be cracked. So the way we handle this one, like a kind of vertical breathing of the structure or horizontal breathing of the structure, we'll see some example later, or we can make the pile flexible. That's why in the middle there is a free body for this one, integral abutment bridge. So basically this KT is the translational stiffness of the pile that basically allow the translational movement. So basically it is the balance between simply supported and the fixed and bridge, and this has to be basically tuned to get the effect to allow the movement, as well as the demand of the pile, flexural demand basically of the pile. So this is a example of a rigid integral abutment bridge. It is basically the arch bridge, but it is also a rigid integral abutment bridge. That means our abutments are fully rigid. It cannot allow the thermal movement. So where the thermal movement will go? So basically, when it is an arch effect, it basically breathe in vertical direction. So this is a very beautiful bridge designed by Robert Saylor, completed in 1959, almost 65 years old bridge, but looks brand new. I had a chance to visit this place before last year, and this is one of the example for the rigid integral abutment bridge where the movement can allow in vertical direction. And this is another example of the rigid integral bridge, but in this case, the horizontal, the movement, thermal movement accommodate in horizontal direction. This bridge was designed by Matthias Fuller, and it was completed in 2001. It is located in Stuttgart, Germany. And the bridge length is around 119 meter, and the radius is very tight, so 53.7 meter. You see this bridge is a pedestrian bridge, and you see the piers are very slender. So only the load carried by the abutment and the pier carrying the vertical load and allow that transverse movement or thermal effect horizontally. So now this is the fundamental behavior and flexibility of the integral abutment bridges. So so we have to have the backfill soil if we go to traditional integral abutment bridges, and then back wall is supported by the compression only abutment spring, and during the expansion the soil moved and it creates some kind of permanent gap, and that gap allowed to movement in summer, and but if the movement is more than the gap, then the soil engaged with the abut back wall. That's why we use only the compression only abutment spring during modeling. The piles has to be modeled with the tension compression spring, because the when it is a the soil cannot take the tension, but other side of the pile take the compression. That's why we can use compression tension spring in one side. That is the modeling approach we'll discuss later. So this is the free body for the model one, which is basically happening during the winter. That means when bridge contract, there is no soil acting behind the soil abutment. But when it is summer, then this soil is activated as a abutment spring. And in seismic event, if we design this bridge to allow the plastic hinge at this location, but many DOTs or the owners do not allow the in-ground plastic hinge. But for argument, if we go with the plastic hinge here, that means the Model 3 basically the behave like a single curvature. So in that case, in seismic event, we can by hand calculation we can calculate the period and the base shear for preliminary design of the abutment integral abutment bridge. This is the example for the pile and abutment spring. So we need to model the pile with this pile spring. So this is the example for a pile spring from L-pile analysis, but the Midas has a good feature and built-in feature. We can also develop the pile spring from there, but we'll discuss later. But for simplicity, I personally prefer to go with the bilinear curve instead of the multilinear curve. That saves a lot of time in modeling. So we can convert this multilinear curve to the bilinear curve. And then we can model the pile with a constant spring, but most of the cases, the upper around, say, for example, 3 to 5 meter, the pile may differ more than this point. So in that case, we need a couple of iteration. But below that, the pile will remain within this range. For example, in this 25-meter depth, the movement will be remaining in this range. So in that case, we don't need to model the pile for bilinear or multilinear spring to reduce the extra task and reduce the runtime of the model. So this is the about the pile spring, and for the abutment spring. Usually we use the compression only abutment spring with gap and without gap. So most of the cases we'll get the final result from the geotechnical engineer, but it takes some time. So before getting the result, we can start our work. So that the structural engineer can start our work before getting the numbers from the geotechnical engineer. So we can say, for example, use this number. This is the based from the Caltrans manual. So we can use the abutment spring for different type of gap. And then model the pile, and we can also do some our L-pile analysis and get this curve, and then start our work, and then finalize the numbers when we'll get the formal geotechnical report. Now talk about the stiffness and the strength of the pile. That is heavily impacted in the integral abutment bridges. So the flexibility is a relative term. So when we talk about the abutment has to be flexible. So it is basically the relatives. For example, you see this currently in the Canadian code restricted only these piles has to be used for fully integral abutment bridges. So HP pile and the 1 feet diameter unfilled steel pile. So you see the stiffness is very quickly reduced. So it is inversely proportional. Flexibility is inversely proportional to the stiffness, and translational stiffness significantly reduced with freestanding height. So this is the freestanding height. So basically, when we provide the casing, we can consider this is a freestanding height. So you see around 8 to 10 meter of the depth, it becomes plateau. So basically, if we go the bigger diameter or heavy high stiffness pile, that give us a strength, but it also reduce the flexibility very quickly, or reduce the stiffness very quickly when we make it a freestanding height. But on the other hand, if we increase the freestanding height, our compression capacity significantly reduced. For example, in the HP pile, the compression capacity reduced almost 60% if we go freestanding height of 8 meter. So that is also a design challenge. So basically, we have to make a balance between the flexibility and the strength. So that is one of the major requirement for designer to look at the provide the flexibility as well as to have the strength to make it work. So this is a design example check for the HP pile. I think S2 has a similar procedure. So we have to check the pile capacity for the compression and bilinear bending. So I'll not go detail in this formula, but this is very much common formula from the code for the compact section and the flexible section. So S2 has a similar kind of approach. So impact of corrosion. So if we go with the HP pile, so our capacity significantly reduce. Definitely flexibility increases, but the capacity is more concerned in the lifetime of the structure. Because we initially we designed based on the capacity flexibility provided, but if the capacity reduced in 100-year lifetime of the structure, and that is a big concern. So we have to consider the corrosion loss during designing of the HP file. So I presented here the percent millimeter corrosion per face, and then presented you see the 49% reduction of the compression capacity in the strong axis and the 57% reduction in the weak axis for the HP pile. I presented here only for one 360 and 174 section, but other cases is the same. Example of check the concrete pile, which is very much straightforward. We can do the section analysis using any software. Midas has its own tools to design the section analysis. I have done it using the Response 2000. So this is an example for a 610 pile with casing with steel pile and without steel pile, and this is a 914 with steel pile without steel pile. And you see the capacity bending axial and flexural capacity increases significantly when you introduce the steel pile. Now we have done some case study to compare the results. So we use 7 type of model, single span to 4 span up to 200 meter length with NU girder, precast NU girder, and steel plate girder as well. So this is type M1 where I use the 2000 NU girder with a steel single line of HP pile. And this is M3 type M3. We have used the 2.8 meter NU girder with a single line of CIP board pile, 1000 meter. And the in type M4 steel plate girder and 1 meter diameter steel concrete board pile. And now this is very interesting result to compare. So stiffness and the comparison capacity of different pile for 15-meter wide abutment. For 15-meter wide abutment bridges, we need this is the number of pile we can accommodate maximum. And then if we compare with this pile with the stiffness and capacity, if we see here the HP pile is 361.74. We can accommodate maximum 13 pile with 15-meter wide abutment. And then if you see the stiffness is for all piles 50.48 kilonewton per millimeter, and the actual capacity is 55.74. But if we compare this type 3 pile ID type 3 with the type 8 with 1 meter diameter pile, we can accommodate maximum 5 pile based on the 3 pile diameter rule of thumb. And we consider 50% crack section for the concrete pile. And then you see almost similar stiffness we can get. So 50.48 versus 50.24 kilonewton per millimeter, but the actual capacity is almost double. So we can definitely argue that the HP pile is not only a solution to provide the flexibility. We can use the concrete pile to get the similar flexibility but with a higher capacity. The beauty of the concrete is when it cracks, it provides the flexibility without losing the actual capacity. Now the geotechnical capacity and the cost of the pile. See, this is the comparison with the HP pile versus 1 meter diameter of the concrete board pile. We have a significant high capacity, and the pile deformation also, pile head depth from the top to the end of the pile. Lateral soil spring is also varied like this, but in HP pile compared to the concrete pile, we can compare roughly 40% cheaper than the HP pile. So concrete is cheaper, so we can get cheaper pile with the similar flexibility with almost similar or higher capacity. But again, this depends upon the site condition, which pile is appropriate for which location. This is some of the slide I'm presenting here, simplified method of analysis. Before going to the modeling, we can use this chart. So dead load reaction linearly increase with the span. You see, I presented here the I section, the steel plate girder, NU girder, and the box section. Dead load reaction for the light rail bridges is 30% higher than the highway bridges. Life load reaction also linearly increases, but becomes plateau after 30 meter of the simple span. So you see here, it is become also plateau, but it is increasing linearly and then a smooth transition. This is a useful chart can be used for simplified analysis. And the thermal induced moment also linearly increases. You see here summer and winter increases with the bridge length and the stiffness of the substructure and pile foundation. Mm. Now, this is the example for the modeling with the Midas Civil. So 3D finite element model, I presented here only one. So 3 span with a new girder, so 50 meter, 60 meter, and the 50 meter span bridge. I use the soil spring. As I said, my previous slide, I use the linear spring because I understand that the pile will not deform much, say below 5 meter or say 3 meter based on a couple of iteration. But here we can basically do some iteration to increase the, reduce the basically second stiffness to change the pile stiffness. And these are the compression only abutment spring in both sides. And we have to have the casing. That's why this is a freestanding height. So there is no soil spring in this location. And this is the 3D view of the wireframe of this model. Now, the spring support using the Midas Civil. So Midas Civil has four type of spring support. So point spring, as I said previously, I used the point spring support in my model, but that is your judgment call. Well, we go the point spring or the multilinear spring. So now major category is the point spring and the surface spring. Midas has also the feature for the surface spring, so we can provide the soil type and basically it automatically convert the surface spring to the point spring. But this is a one-way task. So when we change the soil type, you have to again either redo this task or you have to calculate the point spring manually in a spreadsheet and change it manually or using the table. So there is a nice feature in Midas Civil, so you can export data from the to the Excel sheet and update and put it back to the Excel sheet so that you can automatically update your point spring. Midas Civil also has a general spring support feature. So in that case, we can introduce a custom spring if needed based on the stiffness matrix. And another beautiful feature is the abutment spring, and the pile spring is an integral abutment spring support. So we can provide the some geotechnical properties, and Midas will automatically generate the multilinear spring. But if we change the geotechnical property, you have to redo again. So that you have to keep in mind. And the spring type has linear compression only and the tension only. So in abutment, we use the compression only spring, and we can use the linear spring or multilinear spring for the pile. So as I said, say for example, this line around 5 meter below, I in all cases I use the linear spring, but I iterate at the top if I see the deformation is more than this point, for example, this point, and then we go another second stiffness and then change it there. But probably in the higher depth, for example, in 25-meter depth, we don't need to change because the deformation will be very low somewhere in this location around 5 millimeter or 10 millimeter. So we don't need to change. So that is to me is much simpler to go with the linear spring instead of the multilinear spring approach. So this is the Midas Civil spring support classification. But if the geotechnical engineer or the design requirement, if we have to use the L pile result, then that is a little bit cumbersome process. But Midas Civil has a MCT command. It's called Midas Civil text command, which is very useful. So we can basically generate this soil spring based on the L-pile result provided by the geotechnical engineer. So how to do that? We can go to the tab, Midas tab, tools, and then MCT command cell, and copy and paste text from the Excel. That basically I created with Excel has some very beautiful command. We can arrange this based on the format, MCT command format. So what is the MCT command format? So this command format, it has to be in the line 1. So command is the force dash deformation function to write at the front, and then line 1 for the function name and function type, either it is symmetrical or non-symmetrical, and the ID of the spring. So for example, so line 1, this is I call it the A1 abutment 1 spring name, and then it is force or moment. It is definitely force deformation. So I call the function type force, and then is it symmetrical? Yes, it is symmetrical. And then ID, that means the ID number of the spring. And then in the second line, we have to basically provide the ordinate xy, x2, y2, x3, y3, and so on. So when we arrange this one, just copy and paste this text to the MCT command cell and then click run, then this function will be automatically generated. The next step is how to assign this function to the pile node. We can also do it using the MCT command, but I see it is very easy to do it using the Midas table. So first we can assign one spring manually in a node and then open the point spring. If we go to this tree menu and open one of the point spring support table and then copy and paste that table to the Excel sheet. This is the copy and paste in the Excel sheet and then modify it. So like the spring type is multilinear and then this is the node number. So we have to arrange the node number accordingly and then in all has to be 0 here and then direction of the vector and then provide the function name here and then we can copy this table from Excel back to the Midas table and then it will be automatically assign all of these function to the model. This is very beautiful feature. So and Midas helpline are very cooperative. So if you have any question, you can open a ticket and they can provide you the response right away. Now the result and discussion. As we see, the desired flexibility of full integral abutment can be achieved irrespective of the material and the section. Up to 55-meter long full integral abutment bridge supported on HP pile can be built for highway bridges. But more than that, we cannot use the HP pile. This length is reduced to 40 meters if we go with the LRT bridge because the LRT bridge is heavier, 33% heavier than the highway bridges. So this span reduced to 40 meters. So this is a limitation for the HP pile. We cannot go beyond that. So, but we can build the up to, for example, 200-meter length integral abutment bridges. So what we'll do? So we have to go to the other option. So larger than designated piles defined in the CHBDC are required to build 55 to 200-meter long full integral abutment bridges for both highway and LRT bridges. And you see here in the top is the demand to capacity ratio. And this is our unit line. So up to 55 meter and 40 meter for the LRT bridges, those are green, but beyond that, all are red mark. That means it doesn't work. But if we use the concrete pile, you see this is the axial and moment curvature, axial and moment interaction diagram. All the dots are inside the interaction diagram. That means capacity wise, it is definitely adequate. Definition of the IBs by the code. So as this is the CHBD definition. So integral abutment bridges are single or multi-span continuous deck bridge with a superstructure integrally connected to flexible abutment. This is perfect. A cyclic joint is provided to end of the approach slab that are integrally connected to the deck. So that is good. But when they are defining the flexible abutment, that is a very limited definition. The flexible abutment is an abutment supported on a single row of steel H piles or steel tubular unfilled piles not exceeding 1 feet diameter or 302 millimeter diameter of the pile. So that is basically restricting the designer to move forward. But in ASTO, the definition is much more broader. ASTO is saying integral abutments are rigidly, monolithically attached to the superstructure and are supported on a spread or deep foundation capable of permitting necessary horizontal movements. That is a very open-ended definition. And integral abutments shall be designed to resist or absorb cliff shrinkage and thermal definition of the superstructure. That is basically the key to the designer. So designer is responsible to accommodate this kind of deformation, and there should be a option and freedom to the designer to do so. And Eurocode is very open. It says integral abutment that is connected to the deck without any movement joint. This is very simple definition. Now, the consequence of unclear code definition. This is one of the example in a bit design concept. Concrete board pile was used, but because of the definition, unclear definition by the code, we are not able to move forward in the final design of this bridge. But on the other hand, in BCMOT, they did not follow the CHBDC definition. They have their own definition. So in BC, recently this bridge was built. It's a three-span bridge and supported on the 2 feet diameter steel pile filled with the concrete. Excuse me. Now, conclusion and recommendation. This study shows that fully integral abutment with 1 meter diameter CIP concrete pile is the best solution for 40-meter to 200-meter long integral bridges for a structural life cycle cost, durability, and aesthetic perspective. But this concept is currently not compliant with the CHBDC clause 6.2 because this full integral abutment type is not supported by steel H pile. The author believed that the code should not prevent the designer from using other pile types unless safety and durability as defined by the code are compromised. And then hereby the author would like to define a fully integral or pin connected semi-integral abutment as an abutment type that is supported on a single row of steel pile or concrete or composite piles that provides adequate flexibility and strength to carry the loads. In contrast, symmetrical abutment with bearings shall be relatively rigid and supported on 2 or more rows of piles to resist bending and shear from active soil pressure in addition to vertical loads. The possibility to further develop and improve integral bridges should not be restrained by strict definition imposed by the code. Therefore, instead, the performance-based design approach should be used to meet functionality, serviceability, durability, and safety provision of the code. Yeah, so that is the end of my presentation. Thank you so much for your patience. Now the floor is open for question.
Thank you so much, Mohammed. We do have a couple of questions. The first one says, a well-known issue with jointless bridges is the ratcheting effect caused by the cyclic, cyclic interaction of the abutment wall and backfill, which can result in significant increase in passive pressure over the time, backfill, settlement, and redistribution of the earth pressure with the depth. Um, a standard PY curve does not account for this long-term effect. Is there an established approach to take this into account?
Yeah, very good question. So basically, is a cyclic movement is one of the issues. So that cyclic movement, especially for the steel pile, we can consider the cyclic movement in a fatigue check, and most of the cases it pass. And as I said, one of my previous slide. So maybe I can share that slide. So if you see here, because of the cyclic movement, we can end up with the permanent gap here. And then this gap can be accommodated by the summer movement. So, but in some cases, the summer movement is larger than this gap. Definitely, it will be restrained by the soil. But as you see here, basically the main issue for the cyclic loading for the steel pile, and definitely we can accommodate this one. And the POI curve is considered in the design. As I said, we can simplify the POI curve to accommodate this movement. And definitely up to 200-meter bridge, we can comfortably design the integral abutment bridges. Nowadays, we have very sophisticated tools. It's not a major problem to accommodate the cyclic load throughout the lifetime of his structure performance.
Okay, the next question asks, do you always include abutment springs in non-seismic load cases or no? For braking forces or thermal movements, do you include abutment springs? And what would you do for modal analysis?
Yes, we always use the abutment spring, compression only abutment spring in our analysis, because if we do not use the abutment spring, we'll lose the axial force effect on the superstructure. So that is very important. But definitely superstructure is supposed to carry that load, but um, if the backfill soil is very rigid, then we'll end up with very high axial force effect on the superstructure, and that must be captured during the analysis. Yeah, and yes, the abutment spring must be considered in the model. And when you do the model analysis, it is automatically captured in the model analysis as well.
Okay. The next question asks, what is the P multiplier applied to the PY curve used for the abutment wall? The reference PY curves were developed for single circular piles. Some assumptions or modifications need to be made to use them to model interaction for a wall.
Yes, exactly. So we have to use the P multiplier, and then usually the geotechnical engineer recommended us to use the multiplier, whether we can use from their raw data, or geotechnical engineer also may provide the after P multiplier with the L-pile analysis data and give it to us. So both way we can capture the P multiplier for different kind of piles.
Okay, and the next question asks, what is the max single span integral what is the max single span integral abutment bridge?
Single span, my experience, I design up to 45 meter span. We can definitely go up to 50 meters with the steel girder, but for the pre-stress NU girder, we can comfortably go with 45 meter.
Okay. Next question says, thank you very much for the informative presentation. I have a question with regards to the design of flexible piles for the integral bridges. Can you comment on the consideration of P delta effect for large horizontal movements due to seismic loads?
Yes, very good question. Yeah, so definitely P delta effect has to be considered due to the very large seismic load, and then the integral abutment bridges, as I just described previously, the that is the abutment spring is the key. So we don't expect the embankment does not or will not collapse during the seismic event. That means the when we have the abutment spring, we don't expect large longitudinal movement. So the P delta effect will be very minimum. But as I said, in other option like isolated integral abutment bridges, we do not have the backfill soil. So in that case, we can expect the large longitudinal movement. So definitely P delta effect is one of the check. So in Canadian code and ASTO also have a basically the 30% rule, which is basically 30% longitudinal plus 100% transverse, or 100% transverse plus 30% longitudinal, or based on the P delta effect, whichever is the governed. So most of the cases, the 30% rule govern. So basically the P delta effect automatically covered in this load combination. Thank you.
Thank you. And then the next question asks, what is your assumption regarding the embedment of the steel casing concrete filled piles to concrete piled caps with say about 100 to 150 mm embedded of the casing? Do you assume full moment capacity of the composite section or and the resulting stiffness from that, or do you reduce the amount?
Yeah, very good question. So we usually if we do not want the capacity, we 100 millimeter embedment is good enough. But 100 millimeter embedment will not provide adequate capacity if we consider the steel casing. For example, in this bridge, in BC, we have to consider the seismic load, and we found, and the client do not want the plastic hinges below the ground. So we had only one option to utilize the full capacity of the casing. So basically, we embedded a full capacity of the casing around half a 750 millimeter inside the abutment. It depends upon the design, and we provided some kind of um, steel uh, to make it a welded stud to make it a composite effect to the abutment. And then we basically was to we are able to keep the bridge in elastic in extreme event, even 24-75 year event. So it depends upon your design demand. So if you want to use the full capacity, as I compare in one of the slide uh, here, you see the capacity is significantly increased. So this, for example, 610 pile, this is without steel, and this is basically the example from that bridge. So you see our demand, the blue dot is outside of the capacity. Basically, it doesn't work. So then we basically introduce or add this steel casing around the pile, and you see the bridge is completely working and remain elastic without forming a plastic hinge in extreme seismic event. So it depends upon your demand. You can embed this steel casing inside the abutment or not to do that, depend upon the situation. Thank you.
Okay, sorry, I was muted.
That's okay.
The next question asks, how do you include the nonlinear springs in an elastic static model? Do you need to use time history analysis for seismic loads?
Uh, it depends upon again the code requirements. So, for example, if it is the performance category 3, irregular bridge, lifeline bridge, for example, in CHBDC, we need nonlinear time history analysis. And in that case, I would recommend to use the nonlinear spring at first a couple of meter, depend upon your initial analysis, and use the linear spring below, because it is unnecessary to provide the non-linear spring throughout the length of the pile. It's time consuming, and the runtime of the model will be higher. So try to avoid that and use only the non-linear spring at the top of the pile, which location is basically the pile movement is exceeding that the plateau point.
Okay, and then the next question asks, when comparing fully integral versus semi-integral bridges, which ones perform better seismically?
Uh, So performance-wise, we can go get the similar performance for both cases. Depends upon the designing, but I personally recommend to go with the fully integral abutment bridge because it's jointless bridge, maintenance-free bridge, so almost maintenance-free bridge. So comfortably, we can design this bridge in even in a high seismic zone up to 200-meter length. And I presented another option, that isolated abutment. That is another good option, because in seismic zone we don't allow any plastic hinge below the ground. So in that case, isolated integral abutment could be a good choice for the designer. Uh, yeah, so this one.
Okay, and then the next question says, great presentation. In your opinion, why is CHBDC being rigid on its requirements to support fully integral abutment bridges only on flexible steel piles, and how can we engineers drive the code panel to reconsider this constraint?
Yeah, very good question. That is actually my question as well, because I face as a practical problem during designing of the bridge in a final stage, because in the bid design, I propose a fully integral abutment with a concrete pile because the HP pile was not working. Uh, Mm, I don't know how it's come from, but probably a mistake. I talked with some bridge committee people, top level people, when I was presenting this presentation in short and medium span bridge in Toronto in 2022. They agree and that they need to do something and revise this definition and keep it open for the designer.
Okay. Next question says passive pressure behind the abutment is a function of movement. How reliable are linear springs to capture force effects in superstructure and substructure?
Yeah, passive force is basically non-linear. That's why in Caltrans you see here in this table they basically classified in different category. But definitely we can use the non-linear spring directly as a abutment spring. But as I said, if we go multilinear spring, the model is becomes heavy. But you can do our judgment if the deformation within this range we can use, say, for example, 15,000 kPa with a zero deformation, or say for 5,000 kPa per meter with a 25 millimeter deformation, or the other number proposed by the geotechnical engineer. Yeah, so definitely we should capture the actual behavior based on the passive force effect in the model.
Okay, and the final question we have for today says, in the case of piles with steel pipes, how is the composite action between the steel pipe and the concrete ensured?
Yeah, good question. So actually, it is not a fully composite action because we cannot provide any stud inside the steel pile. So it is basically a capacity of the concrete and the steel together. So I think Ashton and CHBDC, they both has their empirical formula to calculate the actual demand of the concrete fill steel tube.
Okay, actually, one more question.
No problem.
Sorry, last one. Can you also comment on the cost implications of the substructure for using integral and semi-integral, especially for long bridges?
Yes, definitely integral will be much more economical because when you go to the semi-integral, it's just, for example, in a simply supported condition, in a single span bridge, we have to have a deeper girder. So when you go deeper girder, that means the cost of the girder is higher, and when you go the deeper girder, which is basically the more weight, so that means the increase the foundation cost. So I always go with the integral. Bridges based, which is very good in lifetime cost effective and the performance wise. So definitely always integral bridge will win compared to the semi-integral abutment and conventional abutment bridges.
Okay, that concludes our session. Mohammed, thank you so much.
Thank you so much, Luciana, and thank you so much, the audience. I hope you enjoyed it, and I believe you will be able to convince yourself to go with the integral bridges next time. Thank
Absolutely.
you.
Everybody really enjoyed it. Thank you so much. If anybody has any additional questions or any questions that we missed, please feel free to email us at hello@midasoft.com, and we will share those with Mohammed. But yeah, everybody have a great day and thank you so much for joining us.
Thank you.